let's start with a brief background. So we have the Einstein equations. So the main unknown is a Lorentzian metric. We will focus on the cosmological setting. So that means that the spatial space is closed, compact, without boundary, and will allow spatial dimensions larger or equal to 3. And mainly we're going to talk about either vacuum or coupled to a massless scalar field, in which case the Einstein equations take this nice form. Okay, and as we all know, there is an evolutionary part of this system, which is of wave type, and therefore the initial data are position and velocity. So for the scalar field, it's the initial value of psi along a Cauchy hypersurface sigma, the time derivative, which I denote by phi, and for the metric, there is a geometric characterization, representation of these, the analogous values. So this is the induced metric on sigma and the second fundamental form. And these initial data are not free, as we heard also in previous talks, so that you have to satisfy the constraint equations. So in this situation, they take this form, the following form. And as Cecile mentioned early in the week, so this problem has, this system has a well-posed initial value problem, thanks to the pioneering work of Choquet-Bruhat, and moreover, there is a maximal solution, a classical theorem by Choquet-Bruhat and Gerok, which is unique in the sense that is uniquely determined by initial configurations, okay, and maximal in the sense of inclusion. Okay, and the main protagonists of the talk are the so-called generalized Kasner solutions, which go back 100 years ago to Kasner himself, who found like among the first exact solutions, cosmological solutions. Okay, so so these are defined in a half line cross d-dimensional torus. You can consider other topologies, but for convenience in this presentation, I only use the torus as a spatial topology. And they have this very nice simple form. So they're homogeneous. There's no spatial dependence. These PIs, the Kasner exponents, are constants. The scalar field, when it exists, is a multiple of the constant multiple of the logarithm. And the constraints tell you that these relations have to be true. So you have the sum of the PIs equal to 1, and the sum of the squares equal to 1 minus b squared. And in the case, so we want to exclude the case that one of the Kasner exponents is 1, because then you're in vacuum, the rest are 0, and you get the flat solution, which is not that interesting. And one of the main features of this family of solutions is that they all have a Big Bang, what's called a Big Bang singularity at t equals 0. So the spatial slices, sigma t, they shrink, the volume shrinks as you go to t equals 0. And moreover, the curvature invariants blow up, like t to the minus 2, that's as Anne already mentioned yesterday. And one natural question that, of course, one can ask is whether this type of breakdown is due to symmetries or is it a general new phenomenon. So I guess that, which is due to the special nature of these particular solutions. Okay, and I guess the most general thing that one can say is the celebrated singularity theorems that Michalis also mentioned in his talk. So there are generic conditions on initial data, on sigma, that lead to a sort of breakdown, which is, I mean, in particular, these conditions are satisfied for nearby Kasner initial data. Okay, and what is this condition? So namely, you just require that the past mean curvature is strictly negative along sigma. And then Hawkins' famous theorem tells you that in the past, you're causally geodesically incomplete. This means that if you have a time-like curve, time-like geodesic, let's say, and you follow it in the past direction, this will stop in finite proper time, or let's say finite affine parameter. So this means that you're going to hit, so there is a boundary, a past boundary of the maximal solution, okay? Maximal, globally hyperbolic, so in the sense that also we heard in the previous talks. Okay, and the natural question, unfortunately the theorem doesn't say more, just that the solution is past incomplete. And the natural question to ask is whether this breakdown is related to an actual singularity formation. So does curvature blow up, for example, in this along this past boundary? And the answer is not always. So as Michalis mentioned in his talk, there are some pathological examples, like the Taub knot solution, which are sort of, you can think of them as sort of analogous, but not really to Kerr, that have a compact Cauchy horizon. Which is smooth, and therefore you can extend the solution past that Cauchy horizon, which is the boundary of our maximal solution. This leads to the failure of determinism, as Michalis mentioned in his talk, and this is undesirable from a physical point of view. And then the question is, okay, are these realistic or are they unstable? Okay, and another version, let's say, of strong cosmic censorship that we also heard in Michalis' talk by Roger Penrose is that, well, it supports the scenario where you actually have a singularity. So generic initial data should be past and extendable in sort of the solutions that satisfy Hawkins' theorem, okay? And this initial data, this inextendability, okay, it should be some kind of singularity forming. Okay, so that's the expectation or the conjecture, if you like. Then there's the question, again, we heard in Michalis' talk, some rivaling scenarios. So is it space-like, like in the Kasner solutions or in Schwarzschild, let's say, or is it null? You have a singular Cauchy horizon, which we know now that, for example, in the black hole interior, which is a different context, it's not a cosmological setting, we have a very fantastic result by Lafermos-Luc that says that at least near time like infinity, you will always have a null part of the boundary inside the black hole, okay? However, okay, in the cosmological setting and in the context of Hawkins' theorem, the expectation is that generically this will be a Big Bang singularity. So you will have space-like instead of null. Okay, and if you believe that, then the next question, the next natural question is this Big Bang singularity like Kasner? So how does the solution behave toward that singularity? Does it behave in a monotonic fashion, like in Kasner? Or something else happens, okay? So, and again, expectations, so these are predictions. So in the there's a regime which is called subcritical, I will define it later, where the expected behavior is monotonic. So you should, in particular, the Kasner, generalized Kasner solutions in that regime should be stable. And this is part of the what I want to talk about today. Okay, then there is another, outside of this regime, there is a more complicated actually scenario that is expected to occur, or at least in part, due to Belinsky, Kalatnikov, and Lifshitz, so very influential work in the 70s and late 60s, that propose something very different than the monotonic regime. So I will try to explain a little bit what that is. Okay, and then maybe possibly there are other things that we don't know. So there are, let's say, sort of other, let's say, spiky behaviors or well, something a bit wilder, potentially. Okay, so these are predictions. So that's roughly the conjectural picture. Okay, and let's begin with what I call here Kasner-like singularities. So there's no definition, but you can in the literature, but you can, this is as general as it gets. So you can take this as a definition. So we assume Kasner-like singularity is a singular solution whose Big Bang is at t equals 0 again. Okay, and the asymptotic profile of the solution is given by this, it has this form. Okay, so this is not exactly a solution, but you can think of it as a leading order behavior. Okay, so that's you can say is a definition. So we call it Kasner-like because it is like Kasner, although the Kasner exponents now, pi, they vary in x. So you have different values for different spatial points, as is the coefficient of the scalar field when we have one. And the principal one forms, instead of being coordinate one forms, now they're linear combinations of these coordinate one forms that also depend on space. Okay, and then the Kasner relations have to be satisfied at every point now. Okay, so it is like Kasner in a certain sense. So in particular, it's monotonic along a fixed, let's say, time-like curve. So if you fix the spatial coordinates. Okay, so that's Kasner-like singularity. Okay, and then let's get into some heuristics. So is this type of singularity something general, something that you would expect to see in a generic situation? So in order to see, well, one thing you can do is you can plug it into the Einstein equations to see whether it's consistent. Okay, so you can choose, for example, an orthonormal frame that is adapted to these principal directions, which diagonalizes the second fundamental form of the time slices. Okay, and then you see that Kij is 1 over t, is like 1 over t times the coefficient. And because, thanks to the one of the Kasner relations, if you take the trace, you get exactly minus 1 over t for the mean curvature. Okay, and then the Einstein equations, or at least one form of these, so the second variation equations, or ADM equations, if you like. It's an evolution equation for the second fundamental form. Ricci of not bold-faced G here is the Ricci curvature of the Riemannian metric on the time slices. And this now you can replace by the Einstein equations. So in particular, if you're in vacuum, this should be 0. If you have a scalar field, this should be a product of derivatives of the scalar field. Okay, and then you see that, well, we want to treat this, well, at the heuristic level, we want to treat this as an ODE because, as Rita mentioned, ODEs are our friends. Okay, so if you try to solve, let's say we know we have a solution, you want to solve for k, and you see that the left-hand side, this is an ODE that has a general solution, a constant over t, okay, which is consistent with the behavior that you get when you compute k using the Kasner-like profile. Okay, but using again this profile, you compute this partial Ricci curvature, and you see that there are powers in general for general coefficients of this form, of this type. So you have t to the minus 2, all possible, let's say, algebraic combinations of Kasner exponents with distinct indices. Okay, so these particular combinations. Okay, and then it's very easy. So things are consistent if the right-hand side is less singular than t to the minus 2, because then you integrate and you get something which is less singular than 1 over t. And this sort of confirms the leading order behavior you get by using the ansatz. Okay, but this is equivalent now to these particular algebraic combinations of Kasner exponents being less than 1. Okay, so that is, if you like, the subcritical regime. So if this condition is satisfied, we say that we're in subcritical regime, and in that situation, you would expect monotonic Big Bang singularities, Kasner-like singularities, okay? Of course, again, these are all heuristics, okay? So what does the subcritical regime include? So it includes, for example, Einstein's scalar field. That's why I considered scalar field in the first place, with any spatial dimensions larger or equal to 3. So for example, if d is equal to 3, and the scalar field, the coefficient of the scalar field is such that all Kasner exponents are positive, then it's very easy to see that this condition, the subcriticality condition, is satisfied because you use the first Kasner relation, and any kind of combination gives you 1 minus 2 times some Kasner exponent. And since this is positive, you get something less than 1, okay? Then, okay, a physically interesting case is vacuum, okay, in particular 1 plus 3 vacuum. But then, again, it's easy to see that this subcriticality condition, unfortunately, doesn't hold for 1 plus 3 vacuum. And you can ask, what about higher dimensions? And it turns out a very nice observation due to Desmarais, and Spindel. So these heuristics go back to BKL, okay? But subsequent work by Desmarais and Spindel consider higher dimensions. And, okay, algebraically, you can check that the subcriticality condition is non-empty only if the spatial dimensions are larger or equal to 10. And for some reason, for D less than 10, strictly less than 10, it's violated. Okay, so apparently there is some relation with symmetries of hyperbolic space and string theory. You can ask, why is this 10? Okay, of course, algebraically you compute and it's 10, but okay, there is some intuition behind this. Okay, so there are, for example, there's a nice book by Belinsky and Eno, where they present a very nice mathematical background for this well, situation. Okay. Now, for 1 plus 3, in 1 plus 3 vacuum, again, this is violated. Why? Because the Kasner relations imply that at least one, so 1 exactly, Kasner exponent is negative, so let's say P1. Then you take this specific algebraic combination, you use the first Kasner relation, and you get something larger than 1 because P1 is negative, okay? So this means that this estimate that we wanted for consistency of the Kasner-like behavior is not valid unless, and this is the very nice observation by Kalatnikov and Lifshitz in '63, this particular equation identity is true, okay? So omega 1 is the principal 1 form of the, well, corresponding to the negative Kasner exponent in our situation. Okay, so this is the coefficient, if you like, of this dangerous term, which is more singularity to the -2. And if this happened to be 0, everything's good. And you have consistency of the Kasner-like behavior. However, this imposes an extra restriction, which in general shouldn't, there's no reason for it to be true, on these coefficients of the principal 1 forms,Cij's. And this, if you like, eliminates 1 degree of freedom. Therefore, they concluded that the Kasner-like singularities in 1 plus 3 vacuum are non-generic. And they said, actually, that there's no singularity in a generic situation. But OK, due to Hawkins' theorem and this failure of determinism, this is something bad. So they were alarmed a bit. And then Belinsky joined the team, and they said, OK, no, you have to go back and do something else to get the generic behavior of solutions. And this introduced the famous oscillatory BKL scenario. Okay, so what's going on? So let's go back to the Einstein equations, okay? So if you assume you have Kasner-like behavior in 1 plus 3 vacuum, there is this dangerous power which is more singular than t to the -2 because P1 is negative, okay? And at some point for t small, this term is going to dominate, okay? This means that the ansatz, the Kasner-like ansatz is not valid anymore, okay? So what they say, okay, let's look at, given this Kasner-like ansatz, let's look which term is the dominant one, okay? So this, all right? We throw away all the rest, okay? And we look at the ODE, because again, ODEs are our friends, okay? So we look at the ODE by dropping every other term, and you can actually find an exact solution. And you see that for t less than this critical time, another evolution will happen. But the remarkable observation here is that it's going to be again Kasner-like, but with new Kasner exponents. And in particular, there's a very nice formula for this new Kasner exponents. So they change like that. Okay, and it's easy to check if P1 is negative. You see now that P1 prime, the new Kasner exponent, corresponding new Kasner exponent, is positive. And P2 prime is negative, and P3 prime is positive. Okay, what does that mean? Of course, it doesn't mean that all the way up to t equals 0, you will have this new Kasner exponents, because now P2 prime is negative. Okay, and there's a corresponding term, t to the minus 2 plus 4P2 prime now in the equation, which we had thrown away, that now it's going to dominate as t becomes small. So you go back to this evolution equation. You keep this new term, which you think is dominant, and you throw away all the rest, okay, and you redo the same thing. And you see that there's another critical time, etc., where Kasner exponents are going to change. They change again in the same fashion, so that's very nice, okay? And then, once you have this formula, you can also check relatively easy that this infinite chain of oscillations of Kasner exponent has a certain stochastic, or you could say chaotic behavior, in the sense that it will approximate all possible Kasner exponents, and the probability, let's say, that you're in certain interval of Kasner exponents at a certain time is independent of the initial Kasner exponent that you started with. Is given by some function that's related to continuous fractions studied by Gauss, and there's an interesting story about this infinite oscillations. Okay, so that's the oscillatory scenario, and then they stopped there, and okay, afterwards sort of people picked it up, and okay, it became a little bit too optimistic. They said that the generic singularity should be like that, and but now we know that there are generic situations where you have null singularities, so that cannot be true. And moreover, they didn't check, so nobody checked for consistency, or at least, no, people checked, but not of course, not in a rigorous way, because this is very complicated. Okay, so people started checking, and well, so far, let's say the expectation is that part of the story is described by this oscillatory behavior, okay, maybe large part of the story. So what is the danger here? The danger is that you have very complicated behavior and you throw away all spatial derivatives in a sense, and you study ODEs, okay? So now, if you are, let's say, so this is sigma t, you have t equals 0, okay? You have some very small time, and then you look at, let's say, two past time-like geodesics with very nearby spatial points, x1 and x2, okay? And you see that, or x and x prime, you see that as you go toward very close to singularity, if this is true, okay, and you have chaotic behavior, even the tiny, so if you have homogeneous data, then these oscillations happen simultaneously at every spatial point. But if you have even the slightest discrepancy here on the initial data at some, let's say, t1, close to the singularity, the Kasner exponents here will be very different from this Kasner exponents here. So the spatial derivatives of the Kasner exponents, let's say, well, sort of the terms that you will get that were thrown away in the big L analysis may start to matter. Okay, so that's the danger. Anyhow, so what is known? Okay, so as far as the oscillations are concerned, the only regime where this has been confirmed, at least in part, namely not the chaotic behavior, but the fact that you have certain oscillations, etc. This has been confirmed only in the homogeneous setting. So there's first important work by Ringstrom and then others. But again, everything's homogeneous, and moreover, you have Bianchi 8 or 9 symmetry. There's a ton of numerics, which unfortunately I'm not very familiar with and I cannot cover here, but there's many people who have done numerics and simulations even for BKL. Okay, and again, even in the beginning, where people started doing numerics, in, let's say, some symmetric regimes, they said that generally we see these oscillations, apart from some points where there's a certain spiky behavior, okay, which was not predicted by BKL, okay? And this can be seen clearly in a nice way in this symmetry class called Gaudi, which is very instructive, okay? So this has two symmetries which are surface orthogonal, okay? So you have two Killing fields that are surface orthogonal. And in the case where the Killing fields are orthogonal as well, then you have only Kasner-like behavior, and in fact, the system reduces to only ODEs. In the general case where the Killing fields are not orthogonal, it turns out to be quite more complicated. And the short story is that you have Kasner-like behavior, apart from finitely many points where you have these so-called spikes. Okay, but there are finitely many. And then that's fantastic work by Ringstrom. Okay, and in particular, there are expansions everywhere. So even at these spikes, you can understand the behavior of the solution in an asymptotic way. And you can see that there is a discontinuity in the asymptotic data. So the Kasner exponents sort of jump at that point. Sorry. Okay, so there is a different, let's say, this is all continuous rate of blowup, but along a fixed time-like curve, you have monotonicity. So there is no oscillation, okay? So this is a regime where the oscillations somehow are silenced, but still you don't get completely Kasner-like behavior. So, okay, and then there are other works in physics, constructions of more general spikes. There's even a paper by Hansle, Ugla, and Lim where they call spike oscillations. So they try to combine oscillations with spikes. And so it's fair, I think it's fair to say that, let's say, even at the heuristic level, the complete picture is not fully understood. Okay, so it doesn't stop to BKL, but it is, let's say, part of the larger picture. Okay. And now we go to the regime where we actually, it's most understood, or well understood by now. The regime where you only have Kasner-like singularities, okay? Or, let's say, constructing Kasner-like singularities. So by hand, either by hand or due to the fact that you're in the subcritical regime, you sort of force the singularity to be Kasner-like. And then you study the behavior of the solution, the degrees of freedom, and various things. Okay, so there are three categories, roughly, of results. So we have constructions. Okay, so that means that you prescribe the asymptotic behavior like in the heuristic analysis at t equals 0, and you want to solve for the remainder because it's not an exact solution. Okay, so that involves solving a singular initial value problem for the PDE, not the ODE. And there's many people who have worked on this. So in the beginning, so most works are sort of either symmetric or analytic solutions. But now we sort of understand the construction, let's say, of smooth solutions without symmetries, of Kasner-like solutions. Okay, of course, and then once you construct these solutions, these family of solutions, then the question is, what are the degrees of freedom? How many free functions do they depend on, which will give you an indication of whether these are generic or non-generic. So for example, in 1+3 vacuum, you have 4 degrees of freedom. So you should be allowed to prescribe 4 functions, let's say at t equals 0. If you're not, if you're prescribing less, then perhaps what you're constructing is non-generic. So okay, that's at least an indication. Okay, then there's the other category of results, which has stability of generalized Kasner solutions. So we are in a regime near the exact Kasner solutions. Okay, and we only study this problem in the regime where we expect it to be stable, so the subcritical regime. Okay, and what is the problem? So you prescribe nearby initial data at equals 1, and you want to control the solution in the past and prove that a Kasner-like singularity is forming. Okay, and so this actually, this type of results came, well, fairly recently compared to the others by important work of Rodniansky's spec in the beginning. And now we have, let's say, the complete range of Kasner exponents in the subcritical regime. So you know that these Kasner singularities in the subcritical regime are sort of stable in a certain sense, that the solution is Kasner-like, and the corresponding asymptotic data, like the Kasner exponents of the perturbed solution, is close to the Kasner exponents of the background solution that you perturb about. Okay. Then there are conditional results. So results where you assume you have solution, you impose certain bounds on key quantities like the spatial, let's say, scalar curvature, or the renormalized second fundamental form. So you assume that it's bounded, okay? Certain renormalized variable is bounded, and then you infer that there is Kasner-like behavior, and you sort of try to prescribe more precisely what's going on. Okay. Okay, so maybe now I can tell you, so now I'm going to get a little bit more rigorous. Sorry. So I'm going to try to describe a little bit these first two categories, that we sort of know more about. So constructions and stability. So first regarding constructions, okay? So constructions, let's say, you could say it's sort of more interesting in the regime where you have instabilities. So, okay, don't quote me on that, but it's personal opinion. Okay, you have instabilities, therefore you expect instabilities, therefore you want to find what is the sort of the largest submanifold of solutions which have Kasner-like behavior. So this would be, let's say, the stable submanifold in your dynamics. Okay, and a theorem that we proved with Jonathan last year says the following. So if you have, you prescribe your Kasner exponents, okay, we also assume for technical convenience that they're distinct. You prescribe the coefficients of the CIJs of the principal one forms such that things are legitimate. Okay, there is an additional set of differential constraints that correspond to the momentum constraint asymptotically at equal 0 that you have to take into account. Then once you have that, and these are smooth functions, okay, on the torus, there exists a smooth solution to the Einstein vacuum equations that has the following profile. So these are the sort of the first 3 points are sort of legitimate restrictions. So these have to hold, let's say, for every solution, okay, apart from the distinct Kasner exponent condition. Okay, so these are not additional restrictions. So now, since we said that in 1+3 vacuum there are instabilities, you have to have something that sort of eliminates this dangerous, the instabilities, the 1 degree of freedom that is associated to this dangerous term that causes instabilities. Okay, and it turns out that you have this nice form. So at every metric component, the corresponding power of T is the maximum of the 2 Kasner exponents that's sort of corresponding to the indices I and j. And this turns out, sort of in secret here, this already eliminates the extra degree of freedom. So P1 here will be negative. And if you see, if you take a look at this form, you check that the only power that has the negative Kasner exponent, t to the 2 P1, is only associated to the dx1 squared. Otherwise, it will be something else. So already this assumes that the omega 1 form is a coordinate 1 form. And this sort of already, this takes care of the the dangerous term. So the d omega 1, wedge omega 1 will be 0. Okay. All right, and what is the sort of, okay, flavor, let's say, what is the strategy of the proof? So we have only 2 steps. So the idea is simple. So first you compute an asymptotic expansion of your solution to a large enough order, and then you try to solve for the remainder, sort of using the PDE. And then, okay, if you want to do it in a smooth class or a Sobolev class, you have to prove energy estimates, okay? So it's very convenient to look at the ADM system to compute the expansion, okay? But unfortunately, this is not a good system for energy estimates in, let's say, Gaussian time gauge. So it's not symmetric hyperbolic. And okay, then the idea is that, okay, you look at a different equation to prove the estimates. So first you compute the expansion using the ADM system, and then you look at the second order equation satisfied by the second fundamental form to prove the energy estimates for the remainder, okay? Some of the difficulties include, for example, approximate propagation of the constraints. So the expansion that you compute using the ADM system has also, you need it to be an expansion, approximate solution to the constraint equations, which, for example, is used to derive this equation, so in order for things to be legitimate. Then one other point is that this is not exactly also visibly hyperbolic. So you have a wave part, which is very nice, but there's this sort of strange second order term in the right-hand side, and you have to do something about it. So this, if you don't do anything, this will lead to sort of loss of derivatives in the estimates. But it turns out there is a clever way to deal with this, and then you recover the derivatives by doing elliptic estimates. Okay, so that's the 2 main steps. And then the other part, the other category, so the other type of problem, stability of Kasner singularities, which is also now understood for all sort of admissible Kasner exponents that satisfy the subcriticality condition. So this is legitimate, this is non-empty for the scalar field in system for larger or equal to 3 spatial dimensions, or in vacuum for larger or equal to 10 spatial dimensions. Okay, so if you have a Kasner solution that satisfies this condition, then you can perturb the initial data at t equals 1. You can try to control the solution in the past and prove that a singularity, Kasner-like singularity forms. So we were able to do that with Rodniansky and Speck last year as well, using a CMC foliation. So you define a certain time variable that you expect it to synchronize the singularity at t equals 0. So this is a completely, I mean, analytically, from let's say a method of proof point of view, it's a very different problem from the construction because you don't know what the end state is. So in the construction, you put by hand what the final, let's say, Kasner exponents and principal directions are at t equals 0. Here you don't know them, so you try to find what is the end state. This has to be incorporated somehow in your gauge. And for example, sort of similar to Martin's talk, but a little bit different here, where you sort of, the black hole stability problem, you don't really know what your convergers do. Okay, and then you need to do some kind of, okay, in his case, he needed to refoliate to find what is the right gauge that sort of gives you this convergence. Here, somehow magically, and it's very surprising that it actually worked for all Kasner exponents, you can fix the gauge once and for all. So at t equals 1, you assume you have a CMC slice, and then you automatically, this is sort of preserved, you set up a CMC foliation where the mean curvature is exactly -1/t, like in the heuristics. Okay, and this turns out to be the right gauge that synchronizes the singularity. So this, you don't have to change it ever again. And moreover, it's very convenient for analysis because it gives you, let's say, immediately you can read off sort of the behavior of the homogeneous part of the solution very, very, very nicely. And why is this? Well, okay, maybe I'll mention it later. Okay, and then the conclusion is that you can control the second fundamental form, you can control the time derivative of the scalar field when it exists, and in a way that is consistent with the Kasner-like behavior. So k is like 1/t, etc. And moreover, you have that the spatial Ricci curvature is less singularity to the -2, which is the sort of the crucial estimate that you want for consistency with Kasner-like behavior. Okay, but there's no this restriction, extra restriction on the initial data. So this is as general as it gets. You have all the degrees of freedom, okay? So you don't kill anything. And some of the key ingredients, so we already mentioned the CMC gauge. So this turns out, I mean, this is an elliptic gauge. So you get an elliptic equation for the lapse of your time slices, okay? And elliptic equations have infinite speed of propagation. So this is intuitively, let's say, the reason why you would expect it to synchronize the singularity. So the Einstein equations have finite speed of propagation. So in principle, in a hyperbolic gauge, if you start at t equals 1 and you want to find you want to prove the singularity formation, it will not be t equals 0 in a harmonic, let's say, type gauge. So in a hyperbolic gauge, so it would be like some graph which is close, let's say, to 0. Okay, so if you want to synchronize things, so you would hope that maybe an elliptic gauge would do it, and it turns out to be the case. Then there are some key variables that play a very important role in the problem. So you consider a propagated frame from t equals 1. So you have a certain frame which is adapted to your space-like foliation, okay, and you propagate it, let's say, backwards constantly somehow. So in particular, this frame will not be adapted to the principal directions of the end state. So it can be any frame that you want, which is nearby the background frame. Nevertheless, although it's not adapted a priori to the eigendirections, you can consider a certain quantity which corresponds to the structure coefficients of your frame, okay? And you look at the ODE that it satisfies. And using this CMC gauge, you can read off the homogeneous part of the solution very easily. And this is where these algebraic combinations of the Kasner exponents comes in. So these are the Kasner exponents of the background solution that we perturbed about. Okay, and then you see already that if the subcritical, so the homogeneous part of this variable is less singular t to the -1, if and only if the subcriticality condition is valid. Okay? Okay, there is a right-hand side, so in principle you have a PDE. So here you have spatial derivatives of other terms, etc. But if you regard these as low-order terms, at least at the low order in L infinity, so you get a point-wise estimate that tells you have this type of monotonicity in the sense that the time derivative will matter more than the spatial derivative. So the second fundamental form is like 1 over t, and the spatial variables are less singular than 1 over t. Okay? Of course, in order to confirm that this right-hand side is low order, you have to do energy estimates, you have to close a top order, and you have to do a bootstrap, sort of all that nasty things. And surprisingly, this is the only place where the subcriticality condition is needed. So this is this combination. So in particular, only one combination, right? So the one which is P2 plus P3 minus P1. So this is the only term. So let's say the structure coefficient corresponding to that homogeneous part. The only term that could sort of ruin the proof. Okay, so if this turned out magically to be 0, then everything, the analysis goes through. And then you see that this gauge, this particular framework, these variables and everything, really identifies the one variable that is causing the problem. Okay, but if you assume that it's causing the problem outside of the subcritical regime, okay? Here, if you assume that this coefficient is less than 1, there is no problem. Okay, so that's okay. That's the sort of the main observation. Okay, and I should stop here. Thank you very much for your attention.